Up from where we left off, and of course this is the Thursday session, aiming to finish slightly early before that time. And so we will dig straight into things. We've looked at the processor itself in terms of input into the processor, in terms of the control unit sitting on there. You have some registers, and of course you have the arithmetic logic unit in there as well, and then some output coming out. But we understand most of the time you have the processor sitting there as the brain. So you've got the brain of the computer that does the work for you. Let me give it some shoes, and suddenly I lost my drawing skills. Right, so you've got a brain that's the CPU that does the work for you, but in this case our interest is as a processor. And the code that you write is loaded into memory. So code sits in memory, or volatile memory, or the RAM, or most sometimes you see main memory. And that code is fetched into the processor and executed, and sometimes you can have some results either going back to main memory, or sometimes you can have it going elsewhere. So most of the time the processor is interacting with memory. But in terms of memory, how do we create storage and other things? And I have an activity on there. So this is a continuing slide, so it's like we're jumping straight into a video recording, but let's see whether I can get that up and running for us. And go on to the next one. So in terms of dealing with memory, how do we store place? Are we familiar with a capacitor? So it's just basically a device that stores electric charge. They mostly look like that. So when you pass electricity through a capacitor, it will keep the charge, so it will start storing it in there. And then when you cut off the electricity, it will start discharging it. So gradually you'll have some battery and then discharge it. Similar to like a battery, right? So you can think of it as an electronic component that stores something, stores a charge, just the way a battery works. So you have a transistor that can allow power to go through the capacitor, and if the capacitor is charged, you can consider that as a 1, or if it is discharged, you can consider it as a 0 as well. So because we can store a charge and of course we can discharge, we can have a state of a 1 or 0. And normally that's how the dynamic RAM work, or the DRAM, right? So an example of in here, you see it being charged and of course discharged, and you've got a typical example of a memory on there. So DRAM standing for dynamic RAM, and it makes use of these capacitors to store its information. And because you are storing charge and capacitors lose their charge over time, like if you've not used battery for a really long time, you're likely to find that the battery has gone flat. It's good to refresh it. That's why sometimes you have to physically press the refresh button on your keyboard to make things actually work faster, because they start stalling, they start to get invalid data. So there's the refresh rate in order to keep the charge fresh. So memories do have addresses, like basically specialized locations. So if you want to go to this particular line or a line of memory and this particular bit, you would have an address, mostly hexadecimal representation of this particular memory, so you know how to go to it and access the information. So each memory has its unique address, and also each bit has its unique address as well, right, that you can access. So if we take a typical example, if you consider this as memory cells, this particular data that is stored 144 is stored in address location 16 that can be accessed. So we have looked at, you have the processor, you have the main memory, and of course you have secondary storage devices, so things like the hard disk. So you have hard disk, Mostly you have your OS stored in your hard disk, because you lose your data for the main memory. So things that you don't want to lose, or things that you need reloading, or large files, you store them in the hard disk. So in terms of memory hierarchy, we've mentioned the hard disk, we have main memory, and of course you have cache, which mostly is part of the processor as well. So if you've not heard it before, that is CACHE. And I'm talking about processor cache, right? So with regards to the processor cache, it's like a small memory on that is close to the processor, but small because you can't have more of it, because it's also expensive, and it's used to store recently used data. So in programming terms, if you have things like int, you have an example, int x, and then you write a code saying for just a loop, right? For I equals 0 to I less than, let's say, 20, and then you do an I plus plus. My thing has froze, so I'm just waiting for it to come back. And I know my video has frozen as well, so I'm just going to stop my video and then enable my video again so you can all see me. Right, so if you say you just have a loop and you just want to increment the value of I 20 times, or 20 times for example, and each increment, so each loop you're going to say maybe x, actually increment the value of x is equal to I plus, or let's make it x plus 1 for example. So now two things. It knows that it's going to need the value of I, and it's going to need the value of x quite often, because for each process or each execution or each time it runs I, it will fetch I again, it will fetch I again, and it will fetch x again, it will fetch x again, and that's the latest value of x. So instead of going to main memory all the time, it will just put x and I in the cache, for example, right? Then you have the hard disk. Main memory is, we can't have too much of it. It's not expensive, but not expensive as cache, but it's all faster. Cache is faster than main memory. And then hard drive, of course, is slower than main memory. So secondary storage is slower than the non-volatile one. Okay, so basically secondary storage non-volatile, which means if we cut the power to it, they'll keep the information. You have examples, magnetic tapes, solid states, like the ones you find in Macs. You've got CD-ROMs. These days they are not even used that much in terms of when it comes to computers. Like the latest computers do not even have CD-ROMs. And then you've got DVDs. This partly because of the advent of the flash drive, of course. DVDs, some people still use it to watch movies, but most people now use the cloud services or stream information on videos online and other things. But flash drives more or less taking over, and flash drives make use of USB. I know there are ones that have like external hard drives with some Wi-Fi as well that you can easily connect to your computers. So then, still on the computer system, so basically you have devices, and these devices can be input into your system, and you can be, or can be an output of this out of the system as well. So let's give ourselves examples of input devices. Anybody can want to name something that is not necessarily on the screen at the moment. I'm just gonna pick names randomly. Raj. Hi, Raj.
Hi.
Can you give me some examples of input devices that surround us?
Monitor. Smart screen.
Smart screen, yeah. Smart screen can be an input device in the sense that if I take, let's say, I'll go with, you're talking about the input device. So I'll go with something like a touch screen rather. So on the touch screen, like for maybe mobile phone, you touch, you get information going from your finger into the system. So for input devices, we are looking at devices that send information into the computer. So yes, smart screens, you can touch screens, you can think of mouse, you can think of keyboard, touch screen is sitting there, and then you can think of scanners when you scan, or cameras, also cameras or microphones, which things that we are using to communicate with me. So for you to talk to me, you have to unmute yourself using the push button or the click of your mouse, and which is an input, and then of course you use your microphone to communicate with me. Okay, so other things, you can get information from disk drive as well, CD-ROMs, and then DVDs. So when we look at softwares, we're looking at the software side. We've been talking about the hardware input. We can have examples of output devices. The monitor you are using to see me, the screen, TV screens, projectors project the video outside as well. So things that allow us to retrieve information from the computer. You can think of LEDs, RGBs, all those examples being output devices. Okay, so in terms of software, there are various categories of softwares. We have the application software, which is example of the things we are using now. I'm using PowerPoint. We are using Zoom to communicate because it's an application. And then also things like word processing, games, and also specialized software or softwares that runs. Basically things that you have the executable forms. And then you have the system software. The system software is required for the system to run. Basically, it sort of manages the system. So in terms of enabling the hardware to actually work. So if you're thinking about things like the operating system, you can also think of firmware. So you can write specialist firmware for some hardware devices. Utility programs, and then also, of course, software development tools or SDKs, which you will be using as well. So SDKs write code that allow some specific softwares to communicate with a computer or to run applications, or sit between the application layer and the system layer. So going on to the next step, programs and programming languages. Can I pause here to verify if you have any question for me? Are we happy to continue, or do we actually
All good, sir. Yes,
So we can continue. If you want me to continue, give me thumbs up, so at least I know everything is okay. Okay, so I've got some thumbs up. That's brilliant, right? So we are interested in writing codes, and we want to think about what kind of programs are out there and what kind of programming languages are there to enable us to communicate or to write these programs, right? Because we're thinking of a way that we can get the computer to do stuff for us. Okay, so basically a program is just a set of instructions. We just put the instructions together: do this, do that, do that. Or basically for I, we just saw an example for I equals this, that can be combined with several instructions to create a program for us. So it's a set of instructions that the computer just simply follows, because a computer is just a device to perform the tasks that we want for us. So each time I use this cursor to click something, it's instructing the computer to create a line for me. So we normally start off with an algorithm. So if the mouse is moved, move the cursor. If the left button is pressed and is set to be the left button, then of course start drawing something. So your algorithm is just basically the steps that we need to follow. Okay, so it's just a predefined step. Step 1, do this. Step 2, do that. Step 4, do that. You can think of pseudocode when you think of algorithms as well. Okay, so just an example algorithm for calculating the gross pay. So just a few steps, I'll walk through them. So which is, these steps is, we've got 6 stages for this particular algorithm. And the first step is to display a message on the screen that is asking a question, which is, how many hours did you work? Right, so you take your timesheet, right? So you wait for the user to enter the number of hours they have worked, and then once the user have entered the number, you store in memory. step number 2. So you display a message again on the screen. How do you get paid per hour? So basically you get the hourly pay. Ideally, this should actually be extracted from a database because people can't give their own version of the answers and get more pay, right? So you wait for the user to enter the hourly pay, and once the user have entered the hourly pay, you store in memory as well. Then you multiply the number of hours by the amount that, of course, they get paid by the hour, and then you can display on the screen the money they have earned in that particular time. And of course, this message, of course, will include the results from the previous stage, just for the user to understand how it's being calculated. So these set of steps, when you write it down, when you write down the algorithm, it helps you to write your computer program, because instead of writing the code from scratch or simply copying from somewhere and then tweaking with it, you can think of stage 1. How am I actually going to ask the user to give an input? I know how to ask the user to give an input using C++ or Python, for example. So I can write it down in code, and then I can move on to step 2, step 3, step 4. And if I have time even to make it better, I can make them into functions and coordinate them. So algorithms are quite important as far as programming is concerned. So machine language, we have various stack in terms of the language that the computer actually understands. We have already talked about bytes, and we have talked about nibbles as well, which means we kind of accept that a computer is a digital device, and it mostly stores information or deal with information that is stored in ones and zeros, right? So you've got ones and zero form of information, and we can actually say, like maybe 1011, the higher byte, the higher nibble of a byte, and then maybe 0001, the lower nibble of a byte. We can decide that we are designing a processor, and as far as our processor is concerned, when it sees 001, it will take it as a literal number 1. So this bit is our operand, right? So that's the operand. Let me just shorten it. So that's the operand. It's just to say it's a literal number. But the code or opcode is an instruction. So we decide when it sees 0101 or 1011, it means to load whatever is on the lower byte into memory. So even though this is 101100001, the processor will interpret it as load a literal number 1 into a certain memory location. So this is still machine level, dealing with ones and zeros. This is a slightly higher level because we can read something. At least we can read a load. We can see the number 1. More towards the assembly code. So assembly. If we want to do a multiply, we need another representation for that or something. Or we can have a high level code, something like x is equal to 1, which is the high level code. Why did I write H as a hashtag? So you've got a high level programming language or high level language, which is closer to what human beings understand. And of course, closer to the machine code is the assembly as well. Okay, so back to the notes. So in the previous algorithm, we defined the steps and everything. It is also, of course, not ready to be executed because the machine actually needs instructions to be in the ones and zero format. So machine language is basically ones and zeros. I don't know about you, but I'm not very good at remembering numbers, especially when they're a sequence of ones and zeros, to really identify that maybe this means a load, this is a variable, this is a number to multiply, and especially if I have a lot of these to remember. Okay, so basically instead of doing things in ones and zeros, we make use of programming languages to make life easier. Okay, Rakib, is there a question? If it's a question, you can ask. Rakib, is there a question for me?
Not No, sir.
Okay.
No, it's okay.
Which means you're happy for me to continue. That makes me happy. Right. So in terms of programming languages, we have different types. We have talked about high-level programming language. We've given an example of the low-level ones as well. So low-level things like the assembly language we looked at just one example of assembly language. But mostly assembly language require you to think, understand, or know the hardware architecture itself, because if you know a particular processor, then you can simply say load maybe hash number. I've written in this way, let me go with this particular format, into register location 1, for example, which means I need to know that I can actually make use of register location 1. I need to know how the register is arranged, and we don't always have to know all that. So we have something that is close to maybe while loop, while or for, or x equals s plus 1, or run an infinite loop, and even now some are more even closer to English than normal, right? So we have the low level, which is quite close to the machine or closer to the hardware itself, and we have the low level, and then we have the high level programming language. So going a bit deeper, low level programming language is mostly used to communicate with the hardware directly. So if you look at the hierarchy, when we had the ones and zeros, if you have the hardware sitting there, you've got the low level closer to the hardware, and then you have the high level, which has to go through several stages of abstraction before it eventually gets to the low level and then can go to the hardware to communicate with the hardware. So far, so good. Can you show by emoji or by something so I know we are on the same page? Yeah, someone is partying. Yeah, a few thumbs up. I'm going to wait for quite a few people to make sure at least they are with us and they can still hear me. Okay, so going a step further, picking up the pace a little bit. So we have different programming languages. Luckily, last time I asked, people mentioned they have experience of Java, C++, some have experience of Java. Fortran, a bit outdated or a bit quite old, so most people probably don't learn now. Basic, I think people don't learn now. And there is the Blockly, there is Scratch-like programming in a block format now. There's Python, there's JavaScript, Visual Basic, C++, C, C being quite popular as well. So we have from the high level language to the executable file. So when we write a code in the high level language, what happens? How does it translate to the ones and zeros that can be executed? Okay, so in terms of steps, number one, of course, we create the file containing the program. We use a test editor if you've done some programming before. If not, you write your code using an interface, mostly software development kit or an environment. And during the coding, there are certain things that you may need. Things like I don't need to write the code myself that allow me to actually print to the screen. In order to do that, I need to understand a bit more about the operating system. I need to understand a bit more about dealing with screens, so I can write a software that when I say this a particular instruction, it will output to the screen for me. So if you take C, for example, or C++, for example, we've got things like the C out, right? So which is or the C out. The C out allow us, it's a library already written for us, and we can make use of it from a particular file that already exists when we install the IDE, for example, we install OS. So allow us to write to the screen, and all I have to make use of is the C out. So I already have the function sitting there. So there are certain codes, or you can think of them as APIs, that allow you to basically make use of, and of course these are files or directives that sits there, and you can make use of them or import them into your code. That's before the processor, because they've already been pre-compiled for you. Right, then of course those are included in the file, so you have your own code, and the ones you import because they are written for you that you can make use of. So you include them, both of them combined, and then it will run through a compiler where the compiler will try to translate what you have written into the ones and zeros. But when it's trying to translate that into the ones and zeros that the machine understands, it will look for, okay, this is an include file, so I need to load this file, and even that file also includes something else, and he also included something, he or she included something else from there. So I need to link all these files together so I can have the full functionality as if they are seamlessly one particular line of code, so I can make use of it. So it goes through the linker which connects all these specific things for us. Okay, then it will go through these particular steps a few times, of course, or just once with a button of click. Then if there are any errors, if maybe the syntax error, runtime error, or some runtime error, quite hard to decide to detect, but if there are any errors, these errors will be reported for you, so you see them on the screen. From the video, you've seen some stuff about what the compiler does, and Harun has put his comments. Is still waiting for more people to comment on what they believe a compiler does from watching the video that they just watched. And waiting. Ayodeji, thank you. Inshal Abbas, see people are contributing. That's really good. So from high level to the executable, or to something that the processor understand, or the ones and zeros version, right? And please don't copy and paste from the internet. I said in your own words. So I'm glad people are putting things there. So you write the code, you the programmers write the code. The preprocessor will go through in terms of getting the preprocessor directives and getting them ready to get the modified code with basically combine that with your source code that you have written. So compiler will just put things together, and that will pick all the definitions that you have written on there and compress them into one and have one definition on there. So that will create the object, and of course with the object you have the linker going into to give you an executable that you can basically sometimes just double click and then it will run the code for you. Then you have IDEs. I did get a question about which IDE people should use. If you're on Mac, you're probably going to use Xcode. If you are, you can probably just download Visual C++ as well, Visual Studio, the free version, and use. I think we'll most likely use that. There are so many IDEs available. It's simply an integrated development environment, an environment that allow you to write a code, but it gives you all the tools that you need for writing the code, compiling it, and debugging. Debugging simply means fixing problems in your software or fixing errors in the software that you have written into a single application. So we just mentioned some examples earlier, and those who have written code before have used different examples as well. So a typical example of an IDE, you see the Microsoft Visual Studio symbol sitting on there, so it gives you an idea that this Visual Studio environment. You've got a test editor area where you input your test. In this case, you can see a typical C code. You've got your driver program on there, so let me make it driver program or DP for example. And then you've got tools that allow you to basically add some external files, arrange things for you. So you've got things like header files that you've written in terms of resources, the actual source file. So you've got additional tools that allow you to do some editing and other things. Then you've got typically like writing a Microsoft Word, using Microsoft Word and other things. So you've got other menus that support you or make life easy for yourself. And of course, as we dig into things, we will pick a typical example and then work with. So what is a program made of? Common elements of program. You've got the keywords, keywords that you use, the reserved keywords. I just used one keyword earlier, which is for, so which means that this is reserved and the compiler understands it to mean something. Right, so we can't really redefine or use our own version of for example, we can't use it as a variable because it's reserved, right? And then you've got the programmer defined identifier, something like variables, so giving things nicknames. And earlier I used the variable x and I said integer x earlier. X was an integer. So these are defined by the then you've got operators, things like equal to. I used plus plus earlier, or you can say plus and other things. And of course, you can make use of punctuation, something like semicolon to end the line. Then you have the syntax, which is the arrangement of things or the structure of information. This example program, for example, you've got your preprocessor directives at the top. We can go a bit more into details, but the video you watch also gave you some information as well. You've got some keywords sitting on there specific to this particular language as well, reserved. And then you've got some operators in terms of multiplications and other things. You've got certain punctuations and other things also in there. You see some codes for strings sitting in there. And you do have some variables that user defined as well. So keywords, also known as these reserved words, almost sounds like a repetition because we've gone through them, but they cannot be used for other purposes because they are reserved. So things like using, namespace, int, double, for, while, return, and all those examples. And we have highlighted some of these in the previous session. So you have the programmer defined identifiers, things like variables that take it as nicknames to give to other things. And then the operators, we have gone through them. So things that I've already explained, I'm just going to rush through them. And we've highlighted some punctuations and then the syntax that controls the flow of the code as well. So what is a variable? Variable is just a name that we give to a memory location. And earlier we said this is a container. Think of it as a container, right? So let's say you have a cup, right? And this particular cup has a type. So the type of things it can take. So you have one type that you use for, you have a cup that you use for water. You have a container that you actually use to store money. So when you have money, money goes on into this. So when you give a variable, when you declare a variable, you say, let's give this a nickname, right? So let's call this the water cup. And then we can call that the money cup, for example. So it's just the nickname to a particular memory location. And I can tell that my screen has frozen again. So my camera has frozen. So I'm going to disable and enable it as we go along. Let me make sure we are recording as well. So if you take a program, for example, you have things like hours being nicknames storing the particular location, rate, and then pace, things like being nicknames for memory locations, basic containers. So if you are defining a variable, basically you create that variable at the point where we're creating it. So if we want to call x, which is probably going to be an integer, we can't just use x with the code within the code unless we have actually declared them. So at some point in the code, we have to say we intend to use a variable x that is of the type integer, which means it's going to take positive or negative whole numbers at some point, right? So we have some example here as well. Double, you can have several variables. So hour, rate, and pay all being the double type, and of course separated by commas. So can you ask the question? Sorry? I couldn't. Can you type it in the chat window if that's okay? Then I'll repeat to the class because we can't hear you clearly. Is that all right? Oh, so that's a mistake then. I think you've turned on your camera microphone without knowing. If you have a question, please type in the chat window. Right. No, no worries. It's just that when you listen to the recording, you know the part that you talked and what you said. Right. So we do have various types of data that can be used for variables. So like we said, the cup needs to be of a particular type. We've seen the double, we've seen integer, and we look more at the data types later on as we go on. We've all done some form of number system before, and we kind of know what kind of data it is. So of course, one variable of one data type is not the same as variable of another data type. So in this particular case, the data type here is the double, right? So double specifies the data type that we'll be using. So we're looking at next session, input, processing, and then of course output. So basically 3 steps typically perform when you take the input, things like getting data from a keyboard or typing things in, making sense of that information, and then of course displaying it back to the user or writing it to a file. And of course with coding, we can have graphical representation using various plugins and other things or APIs that enable us, or you can write directly to a file. So the programming process, basically make sure that you clearly define what the program is meant to do. Usually better to use algorithms to write that. Visualize the program that's going to run on the computer. You have to have a clear idea of what you want to do. And then you make use of design tools, of course, such as flowcharts or hierarchical charts or pseudocode. I mean, algorithms always work. Or make use of flowcharts, especially if you're doing hardware stuff like I do, right? Then you check, of course, what you've already written for possible errors, and then also think of the actual coding that you are going to do, and then you compile and then save it. Fix any bugs, and then you go through the process again to make sure that there are no errors before you release it. And of course, you can run the program again, fix bugs, and then you do the final validation and forward it out. So when it comes to the type of programming languages that mostly you find in software engineering, you've got the procedural programming, and then you've got the object-oriented programming as well. I can add another one, which is the concurrent programming, but you wouldn't actually find that unless maybe you are doing hardware programming, right? So concurrent programming mostly you find with hardware programming, but let's stick with things like procedural. You go in step by step, and object-oriented programming, you create various objects that can be called or pulled into your programming language, right? So procedural is focused on the process itself, which is basically what you write in line by line, everything in one code. You still make use of some functions and other things, but it's like from line 1 to line 10, all written in the same format, and you're thinking about the process in terms of what each particular thing does, and in terms of making use functions to process data. Whilst objects, you can think of things like, maybe I intend to write a code that will be managing shops, for example. So I can have a class of a particular type of code that defines something like fruits, for example. So you have something that's called fruits. Within the fruits, which can be called as an object, I can have an orange as a type of fruit. So didn't do well. I should have drawn an orange, and my drawing is rubbish. Or I can have an apple also as a type of fruit, and I'm doing much better now. Nope, still didn't do well. So you can have an object, and then you can make use of these objects into several codes. So in more structured version, where you have several classes with header files and other things, right? So the objects that contain data, it means we can manipulate them. Of course, data can be sent in between objects to define